Okay, this is part 2 of dynamic equilibrium for GCSE and A-level chemistry. A quick summary of video number 1. A system in dynamic equilibrium will oppose change. The position of equilibrium shifts. So, if temperature is changed, you need to check what's exo or what's endothermic. If we decrease the temperature, equilibrium will increase the temperature and it will favour the exothermic. Pressure, you need to check the moles of gas. If we decrease pressure, equilibrium will increase pressure and it will shift position to the side with more gas. Okay, now the bit to remember, this entire thing can be summed up because it's epic. Equilibrium position is changed. Epic. One last condition to do. Concentration. If we increase, now we can pick either, let's say we increase the reactants. Hopefully, so let's say it's by adding more hydrogen. Hopefully you're already getting the hang of this. Equilibrium will oppose that change. Equilibrium will try to decrease the amount of reactants. Remembering it's epic, the position of equilibrium is going to be changed. To decrease the amount of reactants, it has to shift to the right. So equilibrium will shift right. And what that's going to do is it's going to give us more of the ammonia. So the yield is going to be increased. Right. The final part of this topic for just now comes into the real world, where we don't just want a maximum yield, we also want it ASAP. We want it as fast as possible. Now, to get it as fast as possible, we've got to think about rate of reaction. To get the maximum yield, you have to look at the equilibrium. Rate of reaction, the factors will be the same for any given reaction. If you want to pause and just take a moment just now and think, what would you do to the conditions of temperature and pressure to get the maximum rate? So hopefully you came up with the idea that you would increase the temperature no matter what the reaction is to get a higher rate, and you would increase the pressure no matter what the reaction is to get a higher rate. Now, you have a limit from the energy consumption for both of these. And you can put in about the environmental impact of using too much energy, the cost impact. You can also, for pressure, have about the explosion risk if it's too high a pressure. For the maximum yield, however, you cannot just generalize. You have to look at the equation. So we want as much ammonia as possible. Temperature, you need to remember, was all about exo or endo. And it does the opposite of what we want. If we increase temperature, it will decrease temperature. So we have to kind of use reverse psychology here. We want this reaction to move to the right. The forward reaction is exothermic, which gives heat out. To get the reaction to give heat out, we have to decrease temperature. Now, you'll notice here, to get as fast as possible, we want to increase temperature. But to get as much as possible, we have to decrease temperature. If we decrease the temperature too much, the rate would be too slow. So what we have to do is compromise, and we need to use conditions that are not too hot and not too cold. Pressure. Same thing we're going to think through. We want the reaction to go from the left to the right. We want it to go from lots of gas to fewer moles of gas. How do we do that? Well, we increase pressure. If we increase pressure, equilibrium will try to decrease pressure. It will shift from the left where there's more gas to the right where there's fewer gas. Here, the two things are in alignment, so it is done at a high pressure. Right. There's one final factor for us to consider here. Catalyst. I've not mentioned it thus far for yield because simply it has no effect. So don't panic if you see this in an exam question because it has no effect. Whereas a catalyst will provide an alternative pathway with a lower activation energy, and so it will increase rate, and for the Haber process we're going to use an iron catalyst. I hope this has been useful for you all. Thanks very much.